at this point we run into a problem. And it's the same problem that Pythagoras and other people encountered when we tried to solve this problem. We said there's no number, or there's no rational number, that when I multiply them together, I get 2. So in some sense, we have a representation for this solution. What does this actually represent? Well, this is the solution to this problem. Can you see that? Right? Like, we have an equation, we don't have a solution for that, so we create a representation for that. X is equal to root 2 is a solution to this problem. In the same sense, we come to this point here and we say, look, this is something that doesn't really work. This is not something that's defined so far. So we have a representation for this. Unhelpfully, we use the letter I to represent the solution to this problem. Why is that unhelpful? Well, because I stands for what we call the imaginary unit, right? And again, you can think about why they would call it something like this, right? Because it seems like that this shouldn't really exist. Ironically, imaginary units are very real, right? And I want to show you 3 reasons why they are. 3 reasons why they are. The first one is, well, like, what's the problem? The problem is you have this situation. X squared plus 1 is equal to 0. And it's a quadratic equation, right? And how do we usually solve quadratic equations? Apart from like balancing them, we could factorize. Not sure, two things that add to 1, or 2 things that add to 0 multiplied to 1. I don't know that, right? We could use quadratic formula. What happens when we try to use quadratic formula? Yeah, why doesn't it work? So we get
the negative in the square root.
Yeah, so that's the problem that we run into. If I write it like this, maybe it's a bit more helpful to see, yeah? So x is equal to minus b plus or minus square root of 0 squared minus 4 times 1 times 1, all over 2 times 1. And what we get is what Matt said earlier, right? We get this, which we can't really compute. The other thing is we say the discriminant, right? The discriminant tells us how many solutions a quadratic equation will have. What is the discriminant here? Well, it's just the part in the quadratic formula, inside here, right? And so that's going to be -4. And we say if the discriminant is less than 0, what do we say usually? No solutions. And the first reason why imaginary units do exist is because the way that we say that they don't exist is slightly flawed. Really, when we say that there are no solutions, we should be saying there are no real solutions, or there are no solutions that you can find yet. Let me give you a really good example. I saw someone explaining how to do subtraction. It was a primary school kind of lesson, and they were doing something like this, right? Using this grid method, 23 minus 5. We know that has an answer, yeah. But the first thing they said was, hey, let's do 3 minus 5. What do you think they said when they tried to do that? You can't do it. Think back to that, right? A long time ago, a situation like 3 minus 5, they said that you can't do it. Really, they just mean that you can't do it yet, right? You can do 3 minus 5, but it's easier just to say, hey, you can't do it yet, so we borrow, and so we're going to get some answer that way, right? So it's easier to say you can't do it. In the same sense, it's easier to, when we introduce these expressions and equations, to say, well, we can't do that, so we just leave it. Like, there's no solutions. In reality, it does have solutions, but there are no solutions that we can really approach it. That's the first reason why. Can you jot that down for me? That's the first reason why imaginary units actually do exist. It's because the reason why we say that they don't exist is slightly flawed. It's kind of similar to saying, well, negative numbers don't exist because we can't do 3 minus 5, okay? That's the first reason. The second reason is we actually have some tools to get some information about quadratic equations without actually solving them. Let's take this again. X squared plus 0x plus 1 equals to 0. And there's a reason why I've included the 0x there. It's because we learned something called the sum and products of roots, right? We can actually find some information about our roots without actually finding out what they are. Alpha plus beta and alpha times beta, right? What were these again? These were negative b on a and c on a, okay? Interestingly, what happens when you calculate these for this quadratic equation?
For that.
Yeah, what do you get? You get 0 for this one, so the sum of the roots. So keep in mind what we said over here. We said that there really are no roots for this. There's no solutions for something like this. But hang on, when you try and calculate the sum of the roots, apparently you get negative b on a, 0 on 1, that's just going to be 0. And what happens when you calculate the product of the roots? You get 1. So at this point, it seems strange to say, it seems like there's a contradiction, right? We're saying that there's no roots or no solutions that exist, but over here, we're saying that we can do something with the roots. When you add them together, you get 0. When you multiply them together, you get 1. You might be forgiven for thinking, oh, this is just kind of like a mistake or an anomaly. Like 0 and 1s, they're like, it just doesn't work. It's kind of broken. But you can actually try for a lot of quadratic equations. For example, try this one and tell me what the sum and products of the roots are, right? This guy over here. Sum of the roots is -4, and the product of the roots is 5. C on A, 5 on 1, 5. These are just real numbers, okay?
Shouldn't it be 4?
-3, yeah, cool, thanks. 4, yeah, right? So these are just real numbers. So very clearly, using the tools that you guys have, it's clear that there are actually roots to this. There are actually solutions to this, okay? Which seems contradictory to what I say, but I hope you can start to see the picture coming together. This is a flawed way of saying that things don't exist, and this is very clearly showing you with the knowledge that you know that there is something else going behind the scenes. Can you jot that down for me? The third reason we can't actually talk about yet. I'm going to come back to it because we don't have the understanding yet to address it. So far at this point, I haven't really talked about the arithmetic and problems involved. And that's because I've just spent a bit of time talking about the fact that this imaginary unit is something that we can work with. It is definitely there. Let's talk a bit about the powers of imaginary units. So something interesting starts to happen. So usually when you take powers of a number and you increase their powers, right, numbers get bigger, naturally, right? I squared, we're going to define as -1. So that's something that we take as a definition, right? That's how we can solve the quadratic equation that we had before, and it's also how we define this imaginary unit. So I squared is -1. What would I to the power 1 be then?
5.
Right, so at this point, anything to the power 1, we can still write as just I, or whatever it itself is. What about I cubed?
-I.
And how do we get that?
Because I squared is -1,
Yep.
and then it's like I squared plus I to the power of.
Great way to work with things that you have before is use definitions you have to solve future problems, right? So in this situation, I cubed you can write as I squared times I to the power 1, adding your indices, right? And I squared, you know, is -1, and so that's just -I, yeah? I to the power 4?
1.
How?
Because I squared equals -1 times -1 equals 1.
Okay, so again, like using you could use I cubed times I, by the way, but it is easier to define this as I squared times I squared. And so -1 times -1, yeah, we're just going to get +1 there. Can you, for me now, find out these ones? All right, James, what do you got for me?
I got I -1 minus I1.
Okay, so again, just showing me how you did that for this one, I to the power 5. What did you do here?
I kind of like know these ones off by heart.
That's all right. That's good that you did it, yeah.
What I originally would have done would be like either I to the power of 4
Yep.
plus I to the power of 1.
Yeah, +1, yeah, you can do that too, right, using your index law. So I to the power 5 is just equal to I, is that what you were saying? Yep, cool. I to the power 6, Matt, what'd you get?
I just wrote the other. So what I is 6.
Yeah.
I would do -1.
I to the power,
4 times I to the power.
yeah?
Oh,
Yeah, I don't know, which one do you
I
want to
to
use?
4 times
Yeah.
to the 2, which would 4 and 2 give you -1.
Yeah, so we've got 1 times -1 there. So -1.
squared.
Which is also I squared, which is, oh, that's interesting. Angus, what do you got? I to the power of 7. How could we write that? Yeah, let's do that.
Should be negative I.
Negative I, over there, sure. And Emily, last one.
Yeah, just I to the 4 times I to the 4.
I to the 4 times I to the 4. That's interesting. So 1 times 1. This is strange. So typically with numbers, right, when you start increasing their powers, they get much larger. But for this one, what seems to happen? It's like a circle. Let me just box these up so it's really clear. Sorry, this is getting a little messy, but... So it seems like it kind of repeats, right? After iterations of 4. So we got I, -1, -I, 1. And I, -1, -I, 1. And this is my last and potentially one of the most visual ways of understanding why imaginary units do exist. Go back to the problem we had before with the number line. The goal with the number line was saying, let's try and fill out everything we can on this number line. Yeah. I said, okay, we've got our integers. We've got our rationals that fit in between, right? 3 and 2. 3 and 2? No, half doesn't go there. Half goes here. We've got our irrationals that fit in between again, yet again. And so we run into a problem with where do these imaginary units fall into our number line if all of this is filled already?
They exist outside the number line.
They exist, yeah, where would we put them? Like, is this part of the numbers? How can that be part of the numbers? We have a number, like numbers are one-dimensional, right? There's no kind of space that you can use with them. There's no volume that you can calculate with numbers. You can use them to calculate volume, right? But numbers themselves, they're a one-dimensional kind of concept.
Make your own line.
You want to make your own line. Where would we put it? Well, this gives us an idea of where we would put it. If we have iterations of 4 where they repeat, that gives us a very good idea of where we can put them. Right? I'll tell you why. When you think about multiplying something by a negative value, right, how would you describe it? If I've got positive 2 over here and I multiply by -1, right, what's kind of happening with this value in some sense? I've got a value here, and I go to -2 over here, right? What's kind of happening here? Right. I think one way that we commonly introduce is we say we're changing directions, right? We say, oh, right, we just change directions like that. That's one way we can describe it. What this shows is, hang on, if I'm multiplying by something, I squared, and I square something and I get back a negative, can you see the problem that's involved with that? I'm changing direction twice, but I somehow have a negative value. There's nothing that I know that does that, right? Because it should return back to a positive value. You multiply any negative value by itself, and you'll get a positive value, because you're changing directions, essentially. What we then do is we think back to this, where you've got iterations of 4 here, and they're repeating. That gives us an idea of what we can do, right? Rather than defining multiplying a negative number as changing direction, we can think about it as a rotation. How can you do a rotation? Well, if you multiply by -1, we do this. And if I multiply -1 again, I do this. So what does I squared equals to -1 represent? Well, multiplying by I, if you think about multiplying by I, where would that go? That would go, it would go up, yeah. 90 degrees, if you might want to say, right? So you go up, there's your multiplication by I, and you multiply again. That's how you get your negative value. What happens if you multiply again? We're going to keep going, right? Down, and you multiply one more time, you get back to where you started, right? And so that's why we have iterations of 4. We can think about this idea of multiplying by I now, coexisting with the real numbers as a rotation on the number line. And in fact, there is an axis which exists. We call it the imaginary axis. Again, unhelpfully, right? Because these actually are something that are real. The person who came up with these said it's much more helpful to think about them as not imaginary units, but he wanted to call them lateral units, right? Because these are numbers which are existing in a different plane in some sense to these real numbers which are here, okay? We're gonna look a bit more about this later on. We're gonna park that for now, but there's 3 reasons why imaginary units do exist. Now, I know you guys are gonna ask about some real world applications. I have a couple for you, and I've printed off. 1, something called signal processing. So you know those cool little lights that you look at like when audio kind of things peak? They can be made really easy using complex numbers. These guys here, I don't know if you've seen these before, these are called fractals, right? And the way we generate these, one of the really cool ones is called the Mandelbrot set, and you use complex numbers to generate that. But yeah, it seems like at this point, I mean, you just kind of do cool things with them. Like, is there a more clear way of where to see them? And there is. It turns out, I won't give too much away, it turns out there's a surprising relationship between trigonometry and complex numbers, right? When you have AC currents, you can represent them as particular waves, cosine waves or sine waves, right? And when we sum them together, it's very difficult to do that in its Cartesian form. So if you have like y equals to cos something and y is to cos something else, when you want to add these two together, it can become very difficult. Representing them using complex numbers is a very powerful way of doing that, okay?